Hello everyone, this is Professor Ng Chi Kun from Unimas. In this video, I'm going to give you an introduction on reinforced concrete design. So for reinforced concrete, the most widely used material for construction all over the world is reinforced concrete. So meaning that most of the buildings or utilities constructed all over the world, they are using reinforced concrete. So as we know, concrete is very strong in compression, but it is weak in tension. So cracks due to tensile stress will develop and sudden failure when first crack forms. So tensile zone is reinforced with steel bars in that case, so that tensile forces needed for moment equilibrium after the concrete cracks can be developed in the steel bars. So this phenomenon can be explained through the diagrams that I'm showing here. So first of all, we have a beam loaded with loads like this. So this kind of loads on a simply supported beam will create compressive stress across section AA at the top. Okay, over here you have compressive stress there, and then we have tensile stress at the bottom of the beam. So if we cut across section AA and isolate it as a free body diagram like this, then we can see that the stress distribution across section AA looks like what is shown in this diagram here, where you have compressive stress on the top part of the beam, and then we have tensile stress at the bottom part of the cross section. Okay, so we know that concrete is very strong in compression, so this compression part is okay for this beam, but beam tends to crack under tensile stress because the concrete here cannot withstand very high tensile stress. So therefore, we add in reinforcement, okay, to help the concrete here to carry the tensile stress. So when the beam is loaded further until the materials become non-linear, okay, then you see that the concrete beam will crack at the zone where you have tensile stress. So the crack may be more and more when the load is getting higher and higher until the beam fails, right? And then this part of the beam will be subjected to very high compression, and then the part that has cracked cannot carry tensile stress in the concrete, and those tensile stress will be transferred onto the reinforcement. So that is the basic concept of reinforced concrete. Okay. So reinforced concrete structures consist of a series of individual members, as we can see from this diagram here. So all these members interact with each other to form the whole structures, right? So in this case, we can see that there is a slab, okay? Okay, we have slab which is suspended, and then we have also slab on grade. So in this course, we are only looking at suspended slab or supported slab. So sometimes we call this suspended slab as well, okay, or supported slab, right? They are called supported slab or suspended slab because they are supported by beams, right? So you can see that these slabs are sitting on beams, right? So this is your beams here, and this is your beams on the top floor, and then this is the beam at the bottom floor, right? And then on top of that, we have also some smaller beams over here, which we call it joists, right? Or sometimes we call it secondary beams. Okay, so meaning that this beam here, normally we call it the primary beam. Okay, and then all these beams are connected to columns, right? And then the beam will transfer the load to the columns, and then the columns will transfer the load to the footing here, and then the footing will transfer the load into the ground. Okay, so the concept of load transfer is that slab transfer loads to the beam, right? And then beam transfers the load to the column, and then the column transfers the load to the footing, and then footing will transfer the load into the ground. Okay, so on top of that, we still have staircases in the building. So this is the staircase part in this building here. So staircases, they are also supported by walls or by beams. Okay, so staircase is a structural element that is similar to slabs, supported slabs, right? So in design, we have to follow certain design codes. Okay, so the most commonly used design codes for reinforced concrete are as follows. So in Malaysia, we are using Eurocode 2. Okay, so this is published by the European Committee for Standardization, right? So we will be using MSEN 1992, okay, Design of Concrete Structures, Part 1-1, General Rules and Rules for Buildings, right? And then in every code of practice, when we use Eurocode 2, then there will be a national annex attached to it. National annex meaning that is the documents that is only used in the nation that publish this national annex. So Malaysia, we have our Malaysia annex. Okay, so this is called MSEN 1992-1-1 2010 Malaysia National Annex to Eurocode 2 Design of Concrete Structures Part 1-1 General Rules and Rules for Buildings. Okay, and then another very common code used worldwide is the American Concrete Institute codes, but we will not cover this code of practice in our course. Okay, so in order to use Eurocode 2, we have some other complementary documents that we need to use. So first is Eurocode. So this document sometimes is referred to as Eurocode 0 as well. Okay, so either we call it Eurocode or Eurocode 0, and then this is also published by European Committee for Standardization. Okay, so this document is called MSEN 1990-2010. So this is basis of structural design, and accompanying this document we have the national annex for Malaysia as well. Okay, and then we have Eurocode 1, also published by European Community for Standardization. Okay, so this is the code number MSEN 1991-1-1 2010. So this is actions on structures, right? Also part 1-1. And then we also have the national annex for Malaysia as well. Okay, and then the old code of practice that may still be used in Malaysia is as follows, which is BS at 110. So in some part of the Eurocode 2, we cannot find the recommended analysis method. So we still refer back to BS at 110 for the analysis method. Yeah? Okay, so this document was used in Malaysia, okay, and is still being used by some of the practitioners out there. Okay,
So BS8110 has 3 parts. So part 1, part 2 and part 3. So the most used is the part 1 of BS8110. Okay. So in reinforced concrete design, the main materials are concrete and reinforcing steel. So concrete is a composite material composed of aggregate, generally sand and gravel, and then they are chemically bonded together by hydrated Portland cement. So the aggregate generally is graded in size from sand to gravel, with the maximum gravel size in structural concrete commonly being 20 mm, although 10 mm or 40 mm aggregate may be used as well. Okay, so the most common type of aggregate used in Malaysia is 25 mm aggregate. Okay, so the strength of concrete is defined by 28-day cube strength of 150 mm cubes. Okay, according to the UK standards. So Malaysia will also follow UK standards. Okay, so sometimes we use smaller cubes, which is 100 mm cubes. Okay, if our aggregate size does not exceed 25 mm. So as I mentioned, in Malaysia, normally we use 25 mm aggregate size. So in that case, we may use smaller cubes as 100 mm cubes. But in practice, normally we use 150 mm cubes. In this case, we just try to avoid confusion among the practitioners, right? And then since the implementation of Eurocode, cylinder strength of 150 mm diameter by 300 mm height is used simultaneously. Okay, so in this case we have a cylinder of 150 mm diameter. Okay, so the diameter is 150 mm and the height is 300 mm. Okay, so this type of cylinder will be used to determine the strength of the concrete as well. But in Malaysia, we mostly use 150 mm cubes. Okay, but bear in mind that there is a conversion of cube strength to cylinder strength. We'll see later on in the lecture. Okay, and then in the US, all the while they have been using the cylinder strength. Okay, which is 150 mm diameter cylinder with 300 mm height. Okay, so generally is not definitely, just generally the cylinder strength is only 80% of the cube strength. But cylinder strength is a better measurement if a concrete core strength from an existing structure is to be compared to the newly batched concrete. So in fact, when we do building assessment, when we do coring, okay, so if we do coring, the shape of the core that we have taken out from the structure is also a cylinder shape. So therefore we'll be comparing apple to apple in that case, if we use cylinder strength. If we use cube strength, then we are comparing cubes to the cylinder core from the structure. So in that sense, we need a conversion factor for that. Okay, so that's why I said the 150 mm diameter cylinder strength will compare better to the core that we have taken out from the building. Okay, so how do we define concrete strength? Okay, so concrete strength is defined as characteristic strength. Okay, so characteristic strength is denoted by the symbol FCK. Okay, and then characteristic strength FCK is equals to the mean strength of the concrete FCM minus 1.64 times standard deviation sigma here. Okay, So normally 1.64 times standard deviation is taken as 8 megapascal for simplification sake. So this characteristic strength is derived from statistics. Okay, so normally if we test a series of concrete strength, okay, so normally we'll get the mean strength here, FCM, right? So meaning that the characteristic strength is somewhere here, FCK, okay, which is at 1.64 times standard deviation, or in this case, we just set it as 8 megapascal. Okay, so in this case, FCK is just FCM minus 8 megapascal. Okay, so that is characteristic strength of concrete. So when we define characteristic strength of concrete, it means that 95% of the time we get concrete strength larger than FCK. Okay, so this is for safety measure. So we make sure that 95% of the time we will get the strength of concrete that we want. Right? Okay, so the characteristic strength is the concrete strength used in the current limit state design. So I'll explain what is limit state design in the next chapter. So in design, the characteristic strength of concrete is denoted by FCK and is shown in this table 1.1 here. Okay, so if we say that the concrete strength class is 12, so meaning that the characteristic strength FCK is 12 megapascal. Okay, so this is cylinder strength. So if one cube strength, then is 15 megapascal. So bear in mind that cube strength and cylinder strength, they have different values, okay, for the same class of concrete. Okay, so the class of concrete follows the cylinder strength, okay, and then the cube strength is a higher value. Okay, so for example, now we said that the concrete strength class is 30. Okay, so meaning that the cylinder strength is 30 megapascal, which is the FCK. Okay, but the cube strength will have to be 37 megapascal. Okay, so this is the effect of shapes, because cubes and cylinders, even if we cast the same concrete into these two different shapes and you take all the samples to test under the compression machine, okay, you'll get two different values. Okay, so generally we will get higher values from the cubes, okay, and the lower value from the cylinders. Okay, so that's why there is a difference in between the cylinder strength and the cube strength for the same concrete. Okay, and then for the tensile strength of concrete is measured from indirect tensile test. So this is what we call as modulus of rupture, as what you have done in your first year laboratory. So a plain concrete beam generally, which is 150 mm by 150 mm in cross section by 750 mm long, is loaded in flexure at the third points of 600 mm span until it fails due to cracking on the tension phase. So the fractional tensile strength FCF from a modulus of rupture test is calculated using the following equation, assuming the concrete is linearly elastic. So this is the equation that we use to calculate the modulus of rupture, as what you have learned in your first year concrete lab. Okay, so when we test concrete under load, okay, if we load the concrete slowly, okay, so we put load on the concrete slowly, the deformation on the concrete will follow this line. Okay, so this is what we call as the stress strain curve for concrete. Okay, and then this tangent here will define the Young's modulus of the concrete, ECM. Okay, so this is the slope of the tangent, okay, which is the Young's modulus of the concrete. Okay, so this is the stress strain curve for the concrete. All right, but in design we try to simplify the stress strain curve. So in this case we simplify into the stress strain curve that is denoted by the dotted line here. Okay, and then in design, okay, in design we are taking the characteristic strength of the concrete and then reduce it by a certain factor to become the design strength of the concrete FCD. Okay, so with a peak stress of FCD equals to alpha CC times FCK over gamma C, the design strength will be given by this equation here. So alpha CC normally is taken as 0.85 FCK, right? And then gamma C is the partial safety factor for concrete in compression. Okay, so gamma C is the partial safety factor, okay, for concrete in compression. So normally is 1.5 for fracture and axial load. Okay, so meaning that the design strength of the concrete is 0.567 FCK. Alright, so that means in design we are only loading the concrete until 57% of the characteristic strength, okay, before the concrete is considered fail. Okay, and then for steel reinforcement, okay, for steel reinforcement as seen in your first year materials lab as well, okay, the steel stress strain curve is given by a linear part in the initial testing, okay, and then you have necking of steel here and then followed by the flat part here, and then it will slowly increase until the steel breaks over here. Okay, okay, so in this case we have the linear part, okay, which we call it the proportional limit part, FP, right? And then Fy is the yielding point, and then Fu here is the ultimate stress of the steel bar that we use in our reinforced concrete. So also in design we have to simplify these curves here, and then normally we simplify into this curve here, okay, alright, and then this U stress of the steel we reduce it to the design stress FYD, okay, so FYK is the characteristic strength of the steel, and then FYD is the design strength of the steel, okay, so FYD is FYK over a partial safety factor gamma S. Okay, so once we reduce the U strength, then it becomes this line here, okay, but for simplification in our course we will just take the B line over here, okay, alright, so meaning that once the steel has reached the design stress, then there is no increase in the stress in the steel, okay, so this part is flat, right? So this will be the stress strain curve that we are going to use in our design calculation. Okay, so the mean value of density may be assumed to be 7,850 kilogram per cubic meter for the reinforced concrete reinforcing steel. Okay, and then the design value of modulus of elasticity. Okay, so modulus of elasticity of the steel is given by this curve here. So this is modulus of elasticity there, which can be taken as 200 gigapascal. Okay, so the application rules for design and detailing in Eurocode 2 are valid for a specific use strength range, which is from 400 to 600 megapascal. Okay, so however, the two most commonly used types of steel are high-use steel and hot roll mount steel inherited from BS at 110. Okay, but unfortunately in Eurocode 2 there is no more hot roll mount steel. Okay, but if you are designing to BS at 110, you still can use hot roll mount steel. Okay, but when we design to Eurocode, we only have high use steel. Okay, so the characteristic use strength of these two types of steel are given in table 1.2 below here. So hot roll mount steel normally is 250 megapascal for the characteristic strength, and high use steel, the characteristic strength is 460 megapascal. But this is only applicable to BS at 110. So if we use Eurocode, we only have 400 to 600 megapascal, which is high use steel. So normally we will be using the average value of 500 megapascal. Okay, so in design normally we use 500 megapascal. So in this course I will be using 500 megapascal for the use strength of steel. Okay, so hence the design use strength is 0.0022. Okay, so for FYD, okay, so FYD is the design strength. So FYD is FYK over the partial static factor, which is the design strength of the steel. Okay, so design strength of steel, if we take this as 500 megapascal, okay, and then normally this partial static factor for steel is 1.15. Okay, so if we take F y d over Young's modulus, that will give us the U strain over here. Okay, so the strain in the steel when the steel start to U. Okay, so this will be 500 over 1.15 and then divided by 200 gigapascal. Okay, so we will get 0.0022. Okay, so that's all for the introductory part of reinforced concrete design. So I'll see you again in the next video. Thank you very much for listening.